Example 7, we're asked to calculate the work done in drawing a string back 40 centimeters. And in part B, we're asked to calculate the slope and determine what it actually represents. So, in the earlier video, we learned that if you needed to calculate the work done by a variable force, where the force is constantly changing, then you can't use the formula work equals force times displacement times cosine of theta because F is not constant. So this formula will not work in this scenario. You see, as the archer pulls back, say 10 centimeters, he's now applying 40 newtons of force, but then if he pulls back to say 20 centimeters, now he's applying twice as much force, 80 newtons, or 30 centimeters, now he's applying a force of 120 newtons. So the force is not constant as he pulls further and further back. So the only way to calculate the work done is to calculate the area under the force versus displacement graph. So first step you would write is the work done is equal to the area under the force versus displacement graph. That's a key point that you must write down. Now you go about calculating that area. So that's the area of this triangle that you can see highlighted. So it's 1/2 times the base times the height. So the base of this triangle would be a length of 40 centimeters, which we're going to change that to 0.4 meters because we want an answer in Newton meters, which is equivalent to a joule. Multiplied by the height of the triangle, and at 40 centimeters, it has a force of 160 newtons. So this will give you an answer of 32 joules of work. Now, what do you think, by the way, what this work represents? When he pulls back on that string, he's actually storing energy. And this stored energy is really what we call elastic potential energy. If we also examine the graph a little bit more, you see you get a nice linear relationship between the force and the displacement. You see, as he doubles the distance from 10 centimeters to 20 centimeters, he doubles the amount of force. So hopefully you can see that the force is directly proportional to the displacement. And this obeys something called Hooke's law that we'll talk about at the end of the video. So in part B, we're asked to tell us what slope represents, and why not let's calculate it. The slope would be the rise all over the run. So in this case, this would be the change in the force, delta F, all over the change in the displacement, delta X. So the force, if we start at 0, 0, the change in that force will be 160 newtons, and the displacement was 0.4 meters. And this will give you an answer of 400 newtons per meter. Now, what does this physically represent? So this is something new. You see, if you had something that was steeper, like we decided to plot a line that was something like this, then that would mean that you have to apply more force over a shorter distance. So it's something about how much force you apply for that distance. This is known as what we call the spring constant. We abbreviate the spring constant with a K. So this is the spring constant. And now the spring constant essentially represents the stiffness of the bow. You see, if that had a larger value and a steeper slope, that means that bow would be even a higher stiffness. All right, so you'd have to apply more force to stretch it. Everything that is elastic has a different sort of stretchability or stiffness to it, and that, if you plot the force versus displacement, that's represented by the slope of the graph. The SI units of the spring constant are traditionally newtons per meter. And again, the spring constant is a measure of how hard you have to stretch or possibly compress a spring. A stiffer spring will have a higher slope, and it will have a higher spring constant.